flipped classroom presentation for Further Maths Unit 5, Hypothesis Testing 2 with small samples. We extend the procedure of hypothesis testing that was introduced in Maths Unit 4 to the testing of, this time, the mean of a normal distribution with unknown variance and estimated from a small sample, usually less than 30. In the previous section, we looked at situations in which the sample was large enough so that the sample variance could be, which is an unbiased estimate of the population variance, could be used instead as a good approximation. For unknown variance, a sample unbiased estimate of sigma squared is S squared, which is defined to be that formula, or that formula, or that formula, and it's the last two that's usually used in calculations, but I prefer the third option. But it depends on the information that you were given in the question. So that's the sample unbiased estimate of the population variance. But if the sample is small, the sample variance does not give a sufficiently good estimate. However, a different distribution called a t-distribution can be used to model the situation in such cases. Now, this distribution was developed by William Seeley Gossett under the pseudonym Students. So it's called Students t-distribution also. The assumptions that we have to make using the t-distribution are that the underlying distribution must be normal. Now, this is reasonable to assume when the distribution arises from a natural population, and that the sample must be random. The method for hypothesis testing using the t-distribution is slightly different from the one you have used previously. You find the test statistic in exactly the same way, but instead of finding the p-value and comparing this with fixed values of 0.05 and 0.01 to choose the appropriate conclusion, you compare the test statistic itself with a critical value, which is obtained from the t-distribution tables. In the test, you will be given the significant level to use. You will then use the tables to find the appropriate critical value according to the significance level, and the number of degrees of freedom, and whether the test is one-sided or two-sided. Now, degrees of freedom we'll come across in a minute. You then compare the test statistic with this critical value, reject H naught if the absolute value of the test statistic is more extreme than the critical value, as you did before with significance level. The t-value depends on the degrees of freedom. Now, the number of degrees of freedom is usually denoted by nu, Greek letter nu, and it's one less than the sample size. This is because for a given value, the mean, n minus 1 of the data items in the sample are free to take any reasonable value, but the value of the last one is fixed if the mean is to work out correctly. So n minus 1 degrees of freedom. Right, let's see an example. A company manufactures electrical components which they state have an average lifespan of 500 hours. An inspector investigates a claim by the company's customers that the components do not last as long as they are supposed to. The inspector tests 15 of the components and finds their lifespan X hours. The results are summarized by, so we've given the sum of X and the sum of each X squared. Test at the 5% level whether the average lifespan of the components is less than the company's claims. We've only tested 15, so that's a small sample. We want to test whether the mean lifespan is 500 hours against that it's less than 500 hours. It's a small sample, we've got 15. Therefore, the sample mean is the sum of X over 15, which is 489.5. 0.2 hours. The unbiased estimate of the variance, we use the same formulas as before. So 1 over n minus 1, 1 over 14 then, sum of x squared minus the sum of x all squared over n. And that becomes 2036.457 and so on. Don't round up too early. Our sample size is 15, so new, our degrees of freedom is 14. Our test statistic, t now, not z, is exactly the same as before. It's x bar minus mu of the square root of the variance of x bar, which is s squared over n. So in our situation, we've got x bar minus 500 for what we want to test for the mean, divided by the square root of s squared over n, giving us minus 0.927. Now that is our test statistic, t. We now look up the tables, and this is on table 7, unless it's on your calculator, and we are looking at 5%, one-sided, so it's the end 5%, so it's going to be 0.95 for x. Its new is 14, so 14 is our degrees of freedom. We're looking at 0.95, so I get the critical value, because we're looking at the left hand side, is going to be minus 1.761. Our critical value is less than the test statistic, so our test statistic is higher than the critical value, so we keep H0. There is not sufficient evidence to support the claim that the average lifetime of the components is less than 500 hours. So for a small sample, we use the T distribution, which is on a different table. Example 2. This is a modified A-level question. The times taken for trains to travel between town A and town B may be assumed to be normally distributed. The train company claims that the mean time taken is 60 minutes. To investigate this claim, the times taken on 10 journeys between the towns are recorded in minutes as follows. State appropriate hypotheses to test the claim, and then test at the 5% significant level whether or not the claim is correct. So we are, our hypothesis is that mean is equal to 60. Now against mean is not equal to 60. So it's going to be two-sided. Our sample is small. We've got 10 in the sample. We need to calculate the sums. They're not given to us. So our sum of x is 621, and the sum of x squared is that value. Our sample mean would be 621 divided by 10, so 62.1. Our unbiased estimate of the variance is s squared using 1 over n minus 1 times the sum of x squared minus the sum of x all squared divided by n, giving us 7.773 recurring. The sample size is 10, so new, our degrees of freedom is 9. Our test statistic is going to be 62.1 minus the 60 we want to prove over the square root of s squared divided by 10 gives us 2.38. So that is what I am given in my sample. I need to compare that with a table. It's two-sided, 5%. So if it's two-sided, I've got 5% either side. So I'm looking up 0.975 with new equal to 9. So 0.975 in table 7. New is equal to 9, so I've got 2.262 as my critical value. Compare the critical value with a test statistic, and we're on, being as our value is on the right hand side, our test statistic is above the critical value, so so we reject H0. There is not sufficient evidence to support the claim that the time taken is 60 minutes. Example 3. The manager of a factory that manufactures a certain type of string claims that its mean breaking strength is 100 newtons. In order to test this claim, breaking strengths in newtons of a random sample of 10 pieces of string were determined with the following results. Small sample. You may assume that this is a random sample from a normal distribution with mean mu and variance sigma squared. Calculate unbiased estimates of mu and sigma squared. Then state a suitable hypothesis for testing the manager's claim using a two-sided test, and then carry out appropriate tests at 5% significance level, giving a reason and state your conclusion in context. So first of all, we need to work out the sums. The sum of x is this, the sum of each x squared is that. So it's a small sample, and our sample mean becomes 99.03. Our unbiased estimate of the variance becomes, using the values, 2.077888, and so on. Don't round up too early. So our hypothesis would be that the mean is equal to 100 against the mean is not equal to 100, two-sided. So our degree of freedom is 9, nu is 9, so we must work out a test statistic first from the observed values. So we get 99.03 for the sample mean minus the 100 that we want to work out over the square root of s squared divided by n, giving us minus 2.13. Our test statistic is minus 2.13. It's two-sided, 5%, so I need to split the 5%. So I look up 0.975 significant level with nu equal to 9. This gives us a critical value of minus 2.262. We're looking at the left-hand side, so we need the minus in. Comparing the critical value with the test statistic, we see that the critical value, that the test statistic is above the critical value, so keep H0. There is not sufficient evidence to support the claim that the breaking strength is not 100 newtons. And that's the end of the presentation on small sample with hypothesis testing.